So this is our review for exam 2. You'll notice as you look at the exam that I have kind of our summary notes on each page and then problems. And we have that for all the different main topics. So we'll just go through. Do you guys have questions? So we'll start with letting you guys ask questions on specific problems, and then if you don't have them, we'll just kind of go through them. So this is problem 23, page 14. So we have packages of sugar bags for sweeter sugar are supposed to have an average weight of 16 ounces and a standard deviation of 0.3 ounces and are normally distributed. Okay, so that kind of sounds to me like that would be for all of the bags, right? That doesn't really sound like a sample. That sounds like everything. Now the company wants to find a sample of 15 bags and check the average weight. So I kind of think that this first part was talking about the population. So for my population, we have an average of 16. So that would be a population mean of a mu. And a standard deviation of 0.3, and it's normally distributed. So it's important you go through that you realize, oh, this is suddenly a switch from our chapter 8, our hypothesis testing things. In this case, I know the population information, and I'm now wondering about the sample. Because now we want to take a sample . Before we actually take our sample, let's do an intermediate step. Now this step isn't necessary. This is just putting everything that we've learned and kind of combining it together. So what if we first looked at just one bag? So a sample size of just one. Okay, and let's let x be the weight of one bag of sugar. Okay. Why would x be a random variable? So remember, a random variable is something that we don't really know what it's going to be in advance. Okay, so why would it be a random variable? We'd say x is an individual observation, okay, but we don't know what it will be in advance, so it is a random variable. Whereas in part B, it has x bar. So what's the difference? So x is just one bag. X bar is the average of 15 bags. So it is the average of a sample of 15 bags. But again, we don't know what it will be in advance. So it's going to be an average, but a sample average, but we don't know what it will be in advance, so it's still a random variable. Let's see, what would the shape of the distribution of the population for all the possible x bars be? So this comes back to our central limit theorem. And the central limit theorem says if you either start with a normal distribution or your sample size is at least 30, then the shape of the distribution for all your possible x bars would be normal. So if the population is normal, or our sample size is at least 30, the distribution of all possible x bars is normal. Okay, so in our case, do we have one of those two things? We have a small sample size, but they did say that my original population is normal, so in our case, it will be normal because our population was normal. What is the mean for all the possible values of x bar? So mu with the x bar means what's the mean for the distribution for all the possible x bar values, but it's always just equal to mu, which is equal to your original population mean, and we said that is 16. And the standard deviation for all your possible sample means is just equal to your original population standard deviation over square root of n. Okay, we said sigma up above is 0.3. So 0.3 over the square root of 15 equals 0.0775. And F, let's see, what is the probability that 15 randomly selected packages will have an average weight in excess of 16.1 ounces? So we're looking for the probability that X bar is at least 16.1. It actually says in excess, so a greater than. Now notice in this case we're talking about 15 packages having an average, so we're talking about X bars. So if we're talking about sample means, you need to use the formula for sample means. So anytime you're trying to find a probability, you have to standardize. But if you're talking about sample means, make sure you use the formula that has an X bar in it. So we have X bar minus mu over sigma over square root of n. And so if you go up several pages to where we have all of the formulas, notice that there's 3 different formulas. There's formulas for individual values, formulas for sample means, and formulas for if you're doing counts or proportions. If you're interested in a probability for sample mean, make sure you pick the one that has an X bar. So in our case, let's plug everything in. The X bar that we're interested in is 16.1. Our population mean is 16. Sigma is 0.0775, and the square root of n, the square root of 15. So Z is going to be 1.29. Does this formula seem very, very familiar? Notice it looks almost exactly the same as what we're doing for a hypothesis test. There's a reason for that. It's because all the math behind it is the same. Hopefully it also makes it easier to do. Okay, so coming back over here, this probability that X bar is greater than 16.1, that would just be the probability that Z is greater than 1.29. And to do probabilities, we had draw a picture and we go to the normal table. Because we've standardized, so it's a Z, so we can use the standard normal table. We're looking for the area to the right. So I have my normal table. We're looking for 1.29. Looks like we're at 0.9015, but that's actually the area to the left, because that table always gives us area to the left. So 0.9015, that means the area to the right is 1 minus that, or 0.0985. So coming back up here, that was 1 minus 0.9015, which equals 0.0985. So we have about a 9% chance of getting a sample with an average greater than 16.1. Probably seems like a while since we've done that, right? Now part G though, notice I'm going to change it up a little bit. So we can do all of this with the same initial setup, okay, but now it's kind of a slightly different topic. It says, what is the probability that one randomly selected bag will have a weight between 15 and 17 ounces? Notice this is talking about one bag, just only one bag. And it doesn't say sample mean or anything because we only have one bag, and with one bag you don't really worry about taking the average. So we're just looking for the probability that X is between 15 and 17 ounces. But notice it's not doing sample means anymore, it's just talking about an individual value. So what you do is go back those 3 pages back, flip back, and notice for individual values you have a formula that just says X minus mu over sigma. Okay, so if you're only talking about an individual value, use the formula that has an X. Now one thing that students have pointed out to me before is what would happen if you accidentally use this formula and you do the square root of n. What's this? If in this case our sample size would be like 1, and taking the square root of 1 is just 1, and will that really change your answer? No. So if you accidentally use this formula, it's not going to make a big difference. But if I come up here and I use this formula and I forgot to divide by square root of n, would that make a difference? That'd be a big difference. So just pay careful attention, make sure you use the right formula. In this case, notice how I'm looking, I have two different x values. I want to know between 15 and 17. That means you need to standardize twice. So for my first one, I'll put my first x value of 15 minus my population mean is 16. My standard deviation is 0.3, so that gives me negative 3.33. For my second one, I put in my x value of 17, keep everything else the same, and I get positive 3.33. So coming over here, I have the probability that x is between 15 and 17, and I'd switch that to the probability that z is between negative 3.33 and 3.33. And once you've standardized, you can just plug you can use the normal table to find those areas. We're looking for the area in between these two numbers. Do you remember how we find the area in between two numbers when you're using a standard normal table? So you go to your normal table and you find the area from 3.33, and that'll give you the area from there all the way over to the left. And then you find the area for this negative 3.33, and it'll give you the area from here to the left. And if you subtract them, it'll give you this part just in between, which is what you actually want. So going to my normal table, 3.33 gives me a 0.9996. So this really big area is 0.9996. And on for my negative 3.33, looks like we're at 0.0004. So those are our two areas. If I subtract them, it'll give me what's in the middle. So 0.9996 minus 0.0004 gives me 0.9992. So we have about a 99.9% chance that the one bag is going to be in between 15 and 17 ounces. Let's skip ahead then to problem 25. This one just kind of has some nice general theory things for the next few questions. Let's say that the true percentage of red M&Ms in a bag is 15%. If 6 students took a sample of M&Ms and recorded the percentage of red M&Ms, which set of values are they most likely to obtain? So when I look at this, before I actually look at those numbers, what would you expect? Okay, if we know that the true value is 15% and you take a sample, what number should you be getting? Should they all be getting exactly 15%? Okay, no, our samples don't match up exactly with the population because it's just a small sample. But should their numbers be close to the true value? Okay, so for samples, we expect to get numbers close to the true value. So expect sample values or sample percentages close to the population percentage. So when I look at my choices here, A has 15, 15, 15, 15, 15. And there's no chance that people are going to do this and get the exactly 15%, and especially that 5 of them aren't going to get the exact same thing. Looks like I only did 5 things here. So that one can't be right because that's all exactly right, and that's not what we expect. We expect some variability. My next one goes from 3% to 90%. If they're really getting those values, they are doing something wrong. Okay, because we're supposed to be close to the population percentage. There's no way that it can be that one. Okay, but C has 14, 13, 15, 14, and 16%. That one seems pretty good, right? Those are all values. There's a little bit of variability, but they're all close to our population percentage of 15%. So I would go with C on that one. On 26, the graph graphs below give the sampling distributions. Now, sampling distributions means all the possible values let's see, for the percentage of red M&Ms. So kind of again talking about those red M&Ms. All the possible values for the sample percentage. Now when we say sample percentage, in our class we talked about proportions. Okay, but a percentage and proportion are the same thing, it's just you have it times by 100. So for all the possible values for the sample percentage, for sample sizes of 70 and 200, and which graph would be which? So what do we know about sampling distributions? We know that if you have a large sample size, they should look normal. Okay, well both of these look normal. We also know that what happened to the standard deviation? The standard deviation got smaller as your sample size got bigger. So the standard deviation gets smaller as the sample size increases. Now when I say the standard deviation, I mean the standard deviation of all the possible values for the sample percentage, not the actual data. And so if your standard deviation gets smaller, you'd be expecting a skinnier graph. So small standard deviation means skinnier graph. So this one is skinnier. So that would mean it must be the sample size of 200. And similarly, which distribution will have a smaller standard deviation? Either A, the population of individual values, or B, the sampling distribution of the sample mean for a sample of size 2. Okay. And again, we'd go with B, because the sample means always have a less variation than the individual values. And we can see that in the formula, the standard deviation for our sample means is always equal to the original standard deviation for all the individual values over square root of n. So it has to be smaller. Then let's turn to number 31, page, I think it's just on the next page. Let's see, we've estimated that 75% of all young adults between the ages of 18 and 35 do not have a landline in their homes and only use a cell phone. We decide to take a random sample of 100 adults and find the sample proportion he had. So when I look at this one, it's estimated that 75% of everyone, that sounds like the population. So the population proportion equals 75%, or 0.75. Looks like on page 10 we have our sampling distributions. Here is our properties for our sample proportions. So the shape will be normal if n times p is at least 5 and n times 1 minus p is at least 5. The mean, so the mean for all your possible sample proportions would be equal to just p, and the standard deviation, again, it's the standard deviation for all your possible sample proportions would be p times 1 minus p over n. So with that in mind, let's go back. So what is the mean of the sampling distribution, or the mean for all the possible values for p hat? So the mean for p hat is equal to just p, which up here, population proportion, that's just p, so 0.75. The standard deviation, so again, this is the standard deviation for all the possible sample proportions we could get, it would be equal to the square root of p times 1 minus p over n. So this would be 0.75 times 0.25 over n. Oh, let's see. We want to take a sample of 100 random adults. So we'll have a sample size of 100. This gives me 0.043. So what is the shape now? So remember, we said it'll be normal if n times p is at least 5 and n times 1 minus p is at least 5. Okay, so n times p equals 100 times 0.75, which equals 75, so that looks good. And n times 1 minus p would be 100 times 0.25, which is 25, so that's also good. So our final answer is that it would be normal. Let's see, let's start with number 2. If you have a right skewed distribution, so first of all, what does right skewed mean? Remember, right skewed means you have a long right tail. We would expect, and then we're comparing the mean and the median. Now when I look at this, if I had just kind of normal distribution, you cut off the tail, then I might say, you know, maybe my median is here, and the mean would probably start off about there. But then this long right tail, remember how that long right tail kind of pulls the average a lot? Okay, and I will always pull the average more than the median. And so my average would kind of get pulled up. So my mean should be bigger than my median. And so because the mean can be pulled a lot, we would say that the mean is not resistant. Okay. What about the median though? Does the median change very much? The median doesn't change very much, so the median is resistant. Now when we say resistant, we just mean it's not going to change a lot due to extreme values or long tails or outliers, but the mean definitely changes. If I was to look at, say, like this distribution right here, number 6, okay. Actually, let's not do number 6, let's do number 5. Okay. What does this one look like? Okay, if I was to sketch it kind of like this, it would seem to have kind of a long left tail, or at least that one way over there is kind of giving the long left tail. So I would say this one is left skew. So number 10, we have a data set for the number of times 25 students ate at the TSC during the year. So here's all of their number of times they ate. We want to create a histogram for our data, and don't forget to label our axes. Okay, so you can see here I kind of give you your lower bounds and upper bounds. So all we have to do is count the number of times each one shows up, and then actually graph it. So my graph over here, I might say the x-axis is the number of times, so it looks like we're going from 23. Oh wait, I already gave you the boundaries. So 20, 25, 30, 35, 40, 45, 50, 55, 60. So this would be our number of times. And over here we'll just do our counts. Maybe we should count them before I decide what my scale will be. So 20 to 24, it looks like we have 4 of them. And 25 to 29 looks like 5. And then 30 to 34 looks like 6. No. 7. And let's see, I counted these before, so let's just write them down. 7, and then we have 4, 2, 1, 1, 1. So we can probably just do a scale, go by 1. So 1, 2, 3, 4, 5, 6, 7. So from 20 to 24, or in this case kind of like 25, I'm just saying we won't include the 25. We have 4 of them. And then our next one has 5, 7, 4, 2, 1, 1, 1. Does this look left skew or right skew or symmetric? Okay, it does kind of seem to be right skew to me. Yeah. And so that's, you know, what a basic histogram would look like. And so I mean, I can't make you draw it by hand on a multiple choice test, but I could give them to you and say which one seems to be correct. Okay. I might ask you to use summary information to create a box plot for the data set. And so in our case, they went ahead and told us what our minimum, first quartile, median, third quartile, and maximum look like. So all I have to do is draw it on. So my minimum is at 23, so sometimes I just kind of go through and make a line at each number. So 23, 26, 32, 37, and 56. Okay, so your middle three are your actual box, and then you just draw a whisker to each one. And when you look at this, it's very obvious from the box plot that that is right skew because you have a much longer right whisker there. So your box plot always has your minimum, and then your first to third quartile is your box with the median in the middle, and your maximum is your last whisker. So our next section is point estimates. Okay, you have your parameter is your population value. Your statistic is your value from your sample. And we'll use our sample statistics to estimate our population parameters. And do you remember what we called bias? This is something that we kind of haven't come back to. Everything else is kind of related, except for the bias. So we haven't talked about it again since we learned it. But an estimate is unbiased if the expected value of your estimate is equal to your population parameter. Otherwise, you'd consider it biased. Okay, and then we have like sample means and proportions. So the sample mean x bar is our estimate of our population mean mu. And the standard error, which we do as s over square root of n, tells us how much our estimate is likely to be off by. And same thing for proportions. Our sample proportion p hat is our estimate of our population proportion p. And the standard error of p hat, square root of p hat times 1 minus p hat over n, tells us how much our estimate is likely to be off by. Because most of the time, an estimate should be within 1 or 2 standard errors of the true value of the population parameter. Let's see, so let's try problem 14 here. If the expected value of x is equal to mu minus 2, and the expected value of y is equal to 3 mu, is x plus y an unbiased estimate of mu? So to see if it is, you have to look at what's the expected value of your estimate. What's the expected value of x plus y? And so for this, we go back to all of our expected value rules we learned so long ago. This would just be equal to the expected value of x plus the expected value of y. And the expected value of x, they told you that up here. That's going to be mu minus 2. And the expected value of y is 3 mu. So if we add these together, we get 4 mu minus 2. Okay, so that's kind of the expected value of x plus y. So now you ask yourself, is this equal to my population parameter that I'm trying to get, which is mu? So is that equal to mu? Well, we have 4 mu minus 2, so that's not going to be equal to mu. So it's not equal to it. So not unbiased. Or if you prefer, that means it is biased. For it to be unbiased, it has to be equal to mu after you do your expected value. So that's kind of our theoretical. Now let's do our more practical example. So let's see, we want to estimate the proportion of U.S. college students who shop on Amazon. So we're talking about proportions. Suppose we take a sample of 150 students and find that 121 of them shop on Amazon. So my sample size is 150, and then we also need to find p hat, the proportion of them that shop on Amazon. So we just say there's 121 of them out of 150 that shop on Amazon, and that's 0.8066. So we estimate 80.66% shop on Amazon. We're also supposed to find the standard error. So that's just up above right here. The standard error is p hat times 1 minus p hat over n. So p hat, 1 minus p hat over n. So 0.8066 times 1 minus 0.8066 over 150 gives me 0.0322. So over here, we estimate that 80.66% shop on Amazon. We're probably within about 3.22% of the true value. Okay, because the standard error tells you how much you're likely to be off by. Because our estimate should be within 1 or 2 standard errors. So we're within like 3.2 to about 6%, depending on how precise you want to be of the true value. So for confidence intervals, there's 2 confidence intervals you guys need to know for this class. There's a Z confidence interval and a T. And again, how do you tell the difference? If you know the population standard deviation, use Z. If you know the sample standard deviation, so if you know your sample standard deviation, you'll use T. And we have one formula to find the sample size for your confidence interval. Notice I only gave you this for the Z because that's the simpler one, and I just kind of made it simpler for the test. Now this review was written for another class, and so I just use Z star and T star instead of the more technical looking notation. It gives you the exact same thing. Let's see, so let's look at 34. Central Middle School has calculated a 95% confidence interval for the mean height mu of 11-year-old boys at their school and found it to be 56 to plus or minus 2 inches. So 54 to 58 inches. Let's determine whether each statement is true or false. So A. Now there will be things like this on the exam because again I want you to understand the meaning. There's a 95% probability that mu is between 54 and 58. This one would be false. Okay. Remember, our true mean of mu is a fixed value. It's not changing. If you had all the information, you could find it. Okay, and it's not changing at all, so you can't talk about a probability for mu. Anytime you see probability for mu, you know that it's going to be wrong. Okay. There's a 95% probability that the true mean is 56. Well, that's almost the exact same thing. It's still saying a 95% probability for the true mean mu, so that would be false. Let's see, C says, if we took many additional random samples of the same size and from each computed a 95% confidence interval for mu, approximately 95% of these intervals would contain mu. That one is correct. So remember, that's what the 95% means. It means if you took lots and lots of samples, the 95% of all the samples you get would actually contain mu. Let's see, D, if we took many samples of the same size and from each computed the confidence interval, approximately 95% of the time, mu would fall between 54 and 58. Okay, this one is completely bogus. We just wrote it kind of the same way. So, mu, again, is not changing. So it can't change whether or not it's in between those two numbers. What does change is the confidence interval that you actually get from your sample data. So based on which sample you pick, your sample mean changes, you get a different sample mean and then a different confidence interval. But mu itself is not changing, so it can't change whether or not it's in that interval. Let's try 35. An agricultural researcher plants 25 plots with a new variety of corn, so n equals 25. Assume that the yield per acre for the new variety follows a normal distribution, so we know it's normal, with an unknown mean of mu and the standard deviation of sigma equals 10. And we want to, let's see, if the average yield is 150, so x bar equals 150, we want to find a 90% confidence interval. So first of all, you have to decide which confidence interval are you going to use. We know our population standard deviation, so we will use a z confidence interval. And also, to use a z confidence interval, you need either normal data or a large sample size. But in our case, it said it's normal, so we can go ahead and do this problem. So our formula for 90% confidence interval is going to be x bar plus or minus z, and let's just call it z star because that's easier than the fancy notation, times sigma over square root of n. So let's come over here to find z star. We want a 90% confidence interval, so that means you'd have 0.9 in the middle. So with 0.9 in the middle, how much is left on each side? 0.05, right? So let's go to our normal table. Remember, at the very bottom, it has some common values. You can use this just a little bit easier. If you want 0.05 in each tail, that means we need a z value of 1.645. So this is 1.645. This is negative 1.645. We just go with the positive value, so z equals 1.645. So coming back over here, I have 150 plus or minus my z star of 1.645 times sigma of 10 over the square root of n. So this is 150 plus or minus 3.29. So we're now going to do hypothesis test. The cost of a 1 carat H colored diamond is $5,600. A Midwestern jeweler makes calls to the contacts in New York City to see if the mean there differs from $5,600. He calls 35 jewelers. N equals 35. The results are sample mean of 5835. He believes the population standard deviation is 520. And we want to know, is the mean different from 5,600? This is obviously a very bored jeweler. So we says conduct a test, and it might also say things like, is the mean different from, and those things are all kind of coming into, you want to do a hypothesis test. So basically, the first thing you just have to figure out is which test am I going to use, and how are you going to figure out if it's a z-test or a t-test? It's the exact same thing as what we did on our confidence intervals. If you get a sigma, or a population standard deviation, you know you have to use a z-test. Okay, so to use the z-test, the first thing we do is check our assumptions, is that it should be either normal or a sample size of at least 30. They didn't say anything about my data, but it does look like my sample size is 35, so we're good. You should choose level of significance. I'll just choose the default of 0.05. You need your null and alternative hypotheses. The alternative is that my mean is not equal to 5,600. So the null would be then that our mean equals 5,600. We'll look at our test statistic, which is z equals x bar minus my hypothesized mean over sigma over the square root of n. So x bar is 5835 minus 5,600 over sigma, which is 520 over square root of 35. This gives me 2.67. For my p-value, we'll use our z-table because this is a z-test. And here we have our 2.67. And which direction am I supposed to shade? Looking at that alternative, that's a not equal to, so this would be the area in both tails. that means we'll have our 2.67, and we'll also do a negative 2.67 and shade to the left and right. So let's go find the area to the left of this negative 2.67 on my normal table. Negative 2.67, looks like we're at 0.0038. So if this is 0.0038, then this is also 0.0038. So my p-value is going to be 0.0038 plus 0.0038, which equals 0.0076. So that's my p-value. How does that compare to alpha equals 0.05? Is that big or small? So alpha is 0.05, so 0.076 is small. So that's going to be a small p-value. So we'll reject our null. And if you reject your null, then that means you have evidence for the alternative. So evidence that mu is not equal to 5,600. Still need more room. I give up. Getting sample mean of whatever our actual sample mean is. Our sample mean is 5835. 5835 or something further away from our 5,600. So number 50 says a hamburger restaurant wants to form a partnership with a potato company. The potatoes come in at supposedly 20-pound bags. Of course, the hamburger restaurant doesn't want to buy an underweight bag of potatoes. Before they sign a contract, they weigh a sample of 40 bags and find an average weight of 19.7 with a standard deviation of 0.1. So this would be like n equals 40, x bar equals 19.7, sigma equals 0.1. They conduct a test to see if the population mean will be less than 20 pounds. So they want to know, is our mu less than 20? Their p-value is 1.35 times 10 to the negative 21. That's a really small p-value, right? And it wants to know which interpretation of the p-value is correct. So remember, the p-value says if null is true, it's the probability of our sample mean, or something more extreme. So if the null is true, that means that the mean would actually be 20. So our actual probability or definition should be something like if mu equals 20, it's the chance of getting a sample mean of whatever we got, 19.7 or less. That's what the p-value should be telling us. So let's see which one is correct. The probability that the true mean weight is 20 pounds is 1.35 times that. Does that sound the same? No. The probability the mean weight is less than 20 pounds is that. Well, no. If the population mean really is 20 pounds, that sounds right so far, then the probability or the chance of getting our sample mean of 19.7 or less is 1.35 times 10 to the negative 21. So that one would be correct. Remember things, but okay, let's see. So there's a few things that we've talked about that'll be on this test. So you have things like descriptive, statistics, and I think those should probably be fairly self-explanatory. I'll ask like, is this left skew or right skew? It'll ask like things about mean or median. And then we have like probabilities. And I'll say things like, find the probability. Or what is the chance? Etc. Okay. And as far as what you're going to have to do on this test, the only thing you have to do to find probabilities is going to come under the normal distribution. Okay. And there's two different kinds that I'll make you do on this test. You'll have it for individual values, which is z equals x minus mu over sigma. And we did one of those today. You also have sample means, and that one will be z equals x bar minus mu over sigma over the square root of n. And then you guys did learn how to do it for counts and proportions, but I think I said, because that's from like 5.3 and 5.4, and I think I said that's not going to be on the test. So it'll either be individual values or kind of like sample means. But it'll say, what's the probability, what's the chance? The next topic is sampling distributions. And sampling distributions will either have the word sampling distribution, or it'll say all the possible values of x bar, or say like p hat. Or even x, which is counts. And so in your sampling distributions, it'll say things like, if we took a sample, what's going to happen? It might ask you what the shape is. And the shape is going to be normal if the population is normal. Or our sample size is at least 30. Okay. And the mean for all of our possible sample means is going to be equal to our original population mean. And the standard deviation is going to be sigma for x bar, which is sigma over square root of n. And of course you have these three formulas for different sets of formulas for p hat, different sets of formula for counts. And tied in with sampling distributions is I might ask you this question, and then I might say, and now find the probability for a sample mean, which means you come up and use this. So the probabilities and the sampling distributions are very tied together. I might combine them on a problem. Then you'll have confidence intervals. And a confidence interval should either have the words confidence interval. Like I can't think of anything that wouldn't have the word confidence interval. And remember, you just have to figure out, do you want to use a z or a t? And we use z if we know sigma, and we use t if we use s. And hypothesis tests should say like a test or determine if like mu equals 30 or mu is greater than 30, etc. So it'll say like test if this is true or determine if this is true, things like that. And for hypothesis test, you either have again a z or a t. And it's z if sigma, t if s. So those are the main things that we learned about for this exam. So that's a great, let's go and add that back in. So sampling distributions is always, if we took a sample, what would happen? And I might not actually say that. I might just say like, what is the sampling distribution or something. But if it's kind of giving you more words and not saying find the sampling distribution, that's kind of the general idea. So if it seems something like that. So we know this about the population. If we took a sample, kind of what would happen?